Okay, we're rolling here. So yeah, this is going to be the last problem class of the semester, and hopefully help you guys get ready for the test. I'm a little bit torn as to what to do because obviously we have the new material, but the old material is probably what's rusty. You haven't done that, so I've got a bunch of problems to try to kind of cover everything. Hit some different things, but just keep in mind, in 2 hours, I'm not going to be able to touch on everything. Absolutely. So don't just assume, well, whatever problems I'm doing is what's important. There's lots of things that are important. I'm not going to focus on memorizing the definitions or the theorems or propositions. That's your job with the flashcards, right? And I'm also not going to focus on the proofs that you are learning, because you can do that on your own and ask questions if you have any, right? What I want to spend my time on is focusing on probably be less than 50% of the test, which is on solving other problems that are using the material, so the applications, because I think that's what's the hardest for everybody, right? Because this is the thing, you just don't know what's going to be there, right? So I'd like to give you some examples to give you an idea of what sorts of things might show up, okay? So I actually went all the way back, kind of towards the beginning of the material to look at some questions that I could ask you. So it's just gonna jump all over the place, just so you know, okay? Which is maybe how taking a test feels anyway, right? You jump from one problem to the next. It's like jumping all over the place. So this is not that inaccurate. But let me start with the first problem here, and this one. This is a really old question, but I just want to kind of get us warmed up. I don't think this one is too difficult, but let's just use it as a warm-up, okay? So here's what it says. Let the set of A sub I such that I is in capital I. So let's take this set. Let's let that be a family of sets, and C also be a set. Okay, so that's what we have, and what I want to do is have us prove that if we take the union of the A sub I, so I'm using my index notation, this goes way back to the first couple of weeks. If I take the union of my A sub i's and I take away C, so this is a set difference here, right? Then I would like to show that that's the same as the union of the A sub I minus C, like that. Okay? So I don't know, we did one quite like this before, but just want to practice. This is not too hard. I'm just going to remind you, we need to remember some of the early material too. Okay? The exam will be comprehensive. Comprehensive final. Okay, so to prove this, what are you going to do?
You should show those subsets of each other.
Correct. The main idea, the overarching outline is we're going to show this is a subset of this, and then this is a subset of this, right? Okay, so we have two parts to this proof, right? We have to kind of do two parts here. I don't know exactly how much room I'm going to need, but let's take this much. And let's try to prove the two parts here. Okay, so to prove that the left side is a subset of the right side, how am I going to start that off?
Element X minus B.
You don't waste any time, Scott. You are straight.
I'm busy, yeah. Go ahead.
So X will be in that union.
Yes.
And X won't be in C.
Okay, so just pick an X on the left side. Pick an X on the left side. So that just means that X is in the union of the A sub i's, and X is not in C, correct? Okay, and now what would we maybe say next? You always want to look what you're trying to prove. You're trying to prove that X is an element of this union over here. So X needs to be in one of these. So what would be my next line?
Since X is not in C, yeah, since X is not in C, then that means that the union of, no, wait.
I'm waiting.
X is in.
Since X in the union
Uh-huh.
of AI,
Yes.
then it is
It's in
in AI for any I in
What, for some I?
For some I.
For some I, right? If it was an intersection, then it would be for all I. Yeah, X is in the union of the A sub I just means there exists an I, right? So there exists, I'm just going to call it I naught, actually. There exists an I naught in capital I such that X is an element of A sub I naught. Okay? Everybody okay with that? All right, so now what?
So X is an A I naught minus C.
X, right. X is an element of A sub I naught, but not in C, correct? And therefore?
It's in
Now it's in the union of all of these, right? So X is in the union of all of these A sub I minus C's. Exactly. Perfect. That look okay to everybody?
Alright, because it's just one more time.
Okay, pretty easy. Okay. This would be, if I gave you this question, I would kind of consider it like a warm-up. That's why we're doing it first today. Now we have to also go the other direction. Okay? So I have to, start with something on this side and prove it's on this side. You can call it X again if you want. If it confuses you to do that, change to a different letter. It's okay. We're starting over. It's like a new proof here, right? Okay, so, you know what? I'm going to change letters just for the heck of it. Okay, I'm going to let Y be an element of the union as I runs through capital I of A sub I minus C. Okay? Is that all right? So it's in the right-hand side. Okay, so what do I say now?
It says I naught and I such that Y is in one of those.
Such that Y is in one of these guys, right? So it would, namely it would be A sub I naught minus C. Exactly. So Y is in A sub I naught minus C. All right, very good. What would be next?
So Y is in the union of AI, but Y is not in C.
Okay, Y is in the union of all of these A sub I's, and Y is not in C, correct? Look okay so far? All right, and therefore, it's in the left side, right? Okay. So Y is in the union of the A sub I's, I in capital I, minus C. Okay? Does that seem okay? This is just a straightforward set theory problem. It goes way back to the stuff we did that we did early on. All right? Okay, we good with that? Can I erase this yet? For anybody watching at home, am I writing big enough for that screen?
Yeah.
People will be able to see it? Okay, perfect. I'm going to go ahead and erase this. If you're watching at home, you can rewind it. And if you're watching right here, you can go on and rewind it too. One of the things that I regret a little bit about this book, I mean, I really like this book. I really like this book. But this book is kind of light on topology. And when different people teach 350, they might teach it with a different emphasis. Some people may spend more time on, but some people don't ever talk about countable and uncountable sets in 350. I chose to do that, but you make choices as an instructor. You have to sacrifice certain things. So I feel a little bad. I didn't really cover any topology. So guess what I can do? I can put it into the test. How do I do that? Of course, if I ask you something like that, I'm going to have to give you in the question a definition. So don't freak out if I ask you. I'm going to give you an example right now. If I give you a definition, it will be something that I expect that you. I'm not going to make it so hard that you couldn't come up with it. I'm going to give it to you and expect you to work with it. Okay, so here's an example. Just want you to see an example of how this might look. Okay, so this is number 2. Okay, define a set U, which is a subset of the real numbers, to be open. See, we never talked about open set. Okay, so it's open if for all x element of U, right, there exists there exists a delta greater than 0 such that the interval x minus delta to x plus delta stays inside of U. I'm defining an open set this way. All right? And then we're going to prove a few things about it. Okay? Do you understand the definition? So if I have a set U, so this is my real number line, I have a set U here, maybe this is U is these points here or something, right? Open just means that if you take any point in U, here's a point that's inside of U, right? Take any point in U, you can make an interval centered at that point, I'm going to call this X, you can make an interval centered at that point that stays inside of U entirely. So of course you just choose your delta small enough here and it stays inside of the whole set U. But that has to be for every X. Okay, so reading these words is so critical, right? This is for all X. There exists a delta. Notice that the delta can change. For this X, I have a delta that works great, but if I had my X way over here by the side, maybe that delta wouldn't be small enough anymore. That's okay, you can change your delta if you need to, okay? So, it kind of makes sense, the definition? See, I would be comfortable asking this because I feel like what's up here in the definition is kind of elementary. It is definitely real analysis oriented. So then let me give you a couple of problems then, okay? So this is actually going to have a few parts, okay? So let's prove that any interval, I'm going to write it like this, open interval AB is open. Let's prove that any interval is open. Okay? So any interval is open. This is why we call it an open interval, okay? Because it fits with this definition. So let's read what we have to prove. We have to show that for every x in that interval, that there exists a delta such that the interval that's centered at x within plus or minus delta stays inside of that interval AB. Okay, so let's do the solution here. Okay, so following the definition, we're going to just let x be an element of the open interval AB. Okay. You know, pictures are always good, right? We can draw our open interval like this. We can put x here. We can put x here. Our job is to convince ourselves that we can find a delta so that the interval centered at x of radius delta stays inside of U. Does anybody have a suggestion how we could find the delta? Because that's our job. We have to show there exists a delta.
Can we just pick the minimum between the distance between x minus b and x minus a?
Exactly. You just, x might be closer to one side or the other. Just choose your delta to be the smaller one, right? You're always, I saw somebody on the last midterm still choosing delta to be the max or something. It's never the max. It's always the min for the delta, okay? So let x be in here. So choose delta to be the minimum, always the minimum, and we can just see from the picture what we're looking at. It's going to be b minus x versus x minus a. Okay? So whichever one is smaller. Okay? And now the claim is that this interval is completely contained in the open interval AB. Okay? So we should check. Whenever you write down the delta, then you want to check that that delta works. Okay? So we're going to check that delta works. This will not take too much work to do this. We're going to check that the delta works. All right. So I have to pick an element that's here and then show that it lives here. Okay. So let's let y be an element of x minus delta to x plus delta, right? And we just want to prove that y is in the open interval AB. In other words, we really need to prove that y is bigger than a and smaller than b. Agreed? Okay, but what we can see here is we already know that y is already bigger than x minus delta, right? And if it's bigger than x minus delta, then it's bigger than x minus both of these things, right? You can subtract either one, and it's going to be true. So y is greater than x minus b minus x, and it's also greater than x minus a. Do you agree with that? In other words, if you take the minimum of these two, right, that means your y is greater than, so if you subtracted the smaller one, then you actually have a bigger expression here. Y is greater than that bigger expression. If it's greater than the bigger of the two numbers, well then it's also greater than the smaller of the two numbers. So it's greater than both of these numbers. This one, of course, just gives me 2x minus b. All right, well that's not really helping me very much. But y is also greater than a, right? So y is greater than a. Does this make sense? Okay, so y is greater than a. That's good. Then we also want y to be less than b. So what do you suppose I'll have to do for that part?
2x plus delta.
Use the x plus delta part of it, right? Go back, basically go back. Here we started off with y greater than x minus delta. Now we can say also y is less than x plus delta because we want to get an upper bound on the y, right? Okay, so y is less than x plus delta, which would imply that y is less than, well, y is going to be less than x plus both of these, either one of them, right? Doesn't matter which one it is. So y is less than x plus b minus x and x plus a minus x. And in particular, the first one tells me, whoops, I turned that around by mistake. The first one tells me that y is less than b. Okay, so we have y is greater than a, y is less than b. All right, so y is in the open interval AB. So that's proving it's open. So again, I never defined that in class, but it's something I can make a problem out of by giving you the definition. You see this idea here? To prove that you live in an interval, you have to be greater than the left side and less than the right side. If you ever had a problem where you had like an a and an infinity, well, then you'd only have to prove that y was greater than a, and then you could stop because the infinity goes forever, right? It would be actually easier in that case. Okay, you guys following what I'm doing here so far? Okay, great. So that's part A. All right, so now here's the second part B here. Are you able to see the whole screen?
Yeah.
Okay, great. Then I'm going to go ahead and write over here then. So for part B, prove that the interval, including the endpoint, so we call this a closed interval, and prove that this is not open. By the way, not open in topology, not open doesn't necessarily mean closed. So I'm not even going to talk about the word closed here because that brings in a whole other definition. So I'm just going to say not open. It does not satisfy this definition. So now this is a great problem to ask you guys for a question because you have to negate this definition. So in other words, you want to show that it is not true that for all points of that closed interval that you can find a delta. Now, how are you going to do that?
Pick the endpoint.
Pick an endpoint, exactly. So choose, very good. So let's choose x equal to, I'll just pick a. It doesn't actually matter which endpoint you use. Choose a, okay. Then basically for every delta is going to fail. Is the idea, okay? So every delta is going to fail. So for every delta greater than 0, right, a minus delta, the interval from a minus delta to a plus delta, if we form that interval, this is not contained in the closed interval AB. So every delta fails. This is you wouldn't even really need to justify that. It's pretty clear. If you really wanted to convince me, you could say something like a minus half of delta is here, but is not here. So something that's here but not here. I honestly, it's very, very, I mean, it should be pretty obvious though. So if I make my closed interval and I choose this point, right, and then I make a delta here, there's definitely points over here that are in the neighborhood of A, but they're not within the closed interval. Does that seem okay? All right, great. Let me ask you a couple more parts. Okay. This would have made a very, very nice test question. I should have saved it. Oh,
You can still put.
I guess I could still ask it.
Yeah,
Still ask
please.
it. I might. You never know. I might.
For the people who don't watch the video,
What's that?
for the people who don't watch the video, come to the study session.
So they'll punish people who didn't take advantage of the
No,
resources.
not punishment. It'll reward the ones that did.
Thank you for being positive. I like that way of saying it. Okay.
Reward us.
Okay. Here is another one. So prove, part C, that Q is not open. Prove that Q is not open. So this is the rational numbers. So can you come up with a counterexample, basically? So the definition for all rational numbers is there going to exist a delta such that the neighborhood around that rational number, that whatever delta you have there, that it's contained in Q. Is that going to work? If it's going to work, then you're saying that the Q is open.
You pick an irrational. You pick.
Pick a rational, right?
You have to pick a rational number. You have to pick a rational number because your set is Q.
Right.
Okay. So, what's your favorite rational number? Huh?
1/2.
1/2, not pi. 1/2. Pi is irrational. So let's take something like 1/2. So let's choose. I mean, it's just like over here. You choose a specific point, right? So choose 1/2. That's fine with me. Okay. I claim that every delta fails, right? Because for every delta greater than 0, if we look at this, if we look at this interval from 1/2 minus delta to 1/2 plus delta, right? The question is this contained in Q? That would be the requirement, right? Is that contained in Q? It's not. This is not contained in Q, right? So for every delta, this interval fails to be contained in Q. What's the reason?
Irrationals are dense.
Say again?
The irrationals are
The
dense.
irrationals are dense, right? So it's the fact that the irrational numbers are dense, not so much that the rationals are dense. It is true, both the rationals and the irrationals are dense, but right now, it's the irrationals being dense that tells me that this cannot be contained in Q. If this was contained in Q, then it would mean you had an entire interval that had no irrational numbers in it. Because it would be contained in Q, right? Everything would be rational. You have an entire interval that has no irrational numbers in it, well, that would mean that the irrationals are not dense. If you go back to the definition of a dense set, which is something you should review, okay, go back to refresh your memory what a dense set is, you're going to see that it talks about having an open every open interval has to intersect that set. Well, here's an open interval that would not intersect the irrational numbers if this was a subset of Q. Okay? Does that make sense? Okay, so I'm just going to say here, since R minus Q is not, is dense in R. And what is my justification for that? We proved it. Exactly. It was done in class. Okay, so proved in class, or it might have been in the homework. I can't remember. It doesn't matter. You don't have to remember like exactly where he's. It was in group work number 7.
That was
I don't have to know those kind of.
That was a theorem, right?
Honestly, I can't remember if it was
an
a.
example.
It might have been an example because I know Q is dense was a theorem.
Oh, never mind.
Yeah,
I think
honestly-
that was an example.
Okay, there's a lot of material for me too. Yeah, the theorem. Yeah, Q is dense in R, and I guess I think it was just an example. I think it just did it as an example. Oh no. It was a homework problem. It was a homework problem. It's 2.3 number 4.
Let's just say that.
Okay, going way back, 2.3 number 4. Okay, so that's proves that. Okay. So far so good, guys. Okay, let's do another one here, part D. I'm milking this for a lot. Okay. It's a nice problem. It's actually a very nice problem. So part D here. Prove if U and V are open, then so is the intersection of U and V. Bye-bye. If U and V are open, then so is U intersected with V. Okay? We have the definition here. So we have to pick an element out of the intersection and show that we can find a delta. Okay? Everybody comfortable with what we need to do here? Okay, so proof. Let X be an element of U intersect V. I probably should say something that, okay, assume that the intersection is not empty. Whenever you start picking an element out of a set, you have to, geez, does the set even have any elements? Because if the set doesn't have any elements, then I've already started off bad here. Okay, but the thing is that the empty set is open.
Right.
Look at the definition. The definition says, for all x in U, blah, 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 blah. Well, if there's no x's in U to begin with, then there's no way for it to fail. There's no way for that. You can't find an x that fails. So the empty set is actually, that's a sort of a side comment, I guess. Side comment over here. The empty set is, this is always open. This is like automatically true. All right. So this is like vacuously true. All right, so assuming it's not the empty set, take an element that is in the intersection, okay? How are we gonna come up with our delta?
It's the minimum of the two deltas.
How are we getting 2 deltas, Noah?
Because X is in U and then X is in V.
Okay, since X is in U, there exists, let's call it a delta 1, right? Call it delta 1 greater than 0, such that X minus delta 1 to X plus delta 1, that interval, is contained in U. This is because U is open, right? So let me just say since U is open. Okay? And similarly, right? Similarly, there exists a delta, since X is in V, right? Since X is an element of V, V is also assumed to be open, there exists a delta 2 such that the interval x minus delta 2 to x plus delta 2, that is contained in V. Exactly. Okay? This is since V is open. Okay, good. So now we take the, what did you say we do for the delta?
The minimum.
Always the minimum of the 2, right? So choose delta equal to the min of delta 1 and delta 2. Take the minimum of the deltas that you found, right? And then we claim that that's going to work, okay? So then x minus delta to x plus delta, that interval, right? Well, if you're taking the minimum delta, then see you have, so here's x, right? You have sort of 2 neighborhoods. Right? So like this is x minus delta 1, and this is x plus delta 1, and this is x minus delta 2, and this is x plus delta 2. Right? If you take the minimum of the deltas, right? So this whole interval is contained in U, and this whole interval is contained in V. So if you stay within the smaller one here, you're inside of both, right? Okay, so this thing is then contained in U intersect V, and you're done. It's pretty clear. It's pretty clear. I don't think you need to like write this up. I mean, you could say, well, let's pick an element here, prove it's here. That's a whole nother thing that I don't think is necessary.
Would you like us to check that one just like we did on the previous one? Or can
I
we-
think this one is really even more clear because, first of all, this delta is equal to one of these two deltas. So one of these two is already just immediately true. And for the other one, your delta is smaller than the interval that you're making for the other delta. So basically this thing would be contained in, I mean, you could do this. These things are judgment calls sometimes, which is why I sit in the front of the room during the final. So if you have a question, you come up and ask me, right? So basically, this has got to be contained. So this has to be contained in that one and in this one, right? Well, actually, so what you could do to prove this is, you could just say, without loss of generality, delta 1 is less than or equal to delta 2. You could just take that as a given. Now, x minus delta to x plus delta is contained in, well, you could actually just say this equals x minus delta 1 to x plus delta 1, right? And so on the one hand, that's contained in u. It's contained in u, but it's also contained in the interval x minus delta 2 to x plus delta 2, which is contained in v. So it's contained in both of them. That's really, overdoing it probably. I think it's pretty clear. So, okay, does that make sense, guys? People good with that? All right, got through that. I could actually ask a few more parts, but I think I'm going to move on. Just, you get the idea here, like what this kind of question would be like. So I just wanted you to see that. But let's move on. I want to get into some other things. I want to make sure we save enough time to practice a lot of stuff.
Professor?
Yes. Oh, yeah, Aaron.
So you talked about actually giving like a topology type question, maybe giving.
Well, that's what this was.
Yeah.
Just to
So
show you.
on the exam, if we just so happen to know a little bit about topology, you probably don't want us using other things from.
Correct. If you happen to know something outside of the scope of the class, don't use it.
Okay.
Definitely don't use it because you could just say the collection of open subsets of R is a topology, and by definition of a topology, it's closed under finite intersections and arbitrary unions, and then that's just like stealing all the fun. Yeah.
Okay.
Yeah. Please be careful. If you happen to know something outside the scope, don't use it, or at least come ask me. You can ask me. It'd be better to ask me during the test than to assume it's okay. Okay. All right. I got another problem here. Let's go on to something new. Number 3. Let's say that assume that A is a subset of the interval from -10 to -1, and B is a subset of the interval from 1 to 10. Prove that the supremum of the set A times B. I'll have to define what that means in a second, but A times B. But let's prove that that's equal to negative of the infimum of capital A times the supremum of capital B. No, this is not what I wanted. Sorry, this is supposed to be the supremum of something else here, sorry. This is supposed to be the supremum of the set absolute value of AB. This is what I meant to write. Absolute value of AB. So let me explain what that means, okay? So I'll give you, this would be given to you, right, the definition, right? The absolute value of AB, by definition, this is the set of the absolute value of little a, little b, such that A is in capital A and B is in capital B. So you do all possible multiplications, and then you You do all possible multiplications and you take all of their absolute values. Okay? So tell me how you like this proof. I have an idea. The infimum of A is negative 10, and the supremum of B is positive 10. So this is negative of negative 10, and positive, that comes out to 100. Okay, so the answer on the right side is 100. On the other hand, if I multiply something from here with something from here, and I take the absolute values of all of those things, and I take the supremum of those, is also 100. So 100 equals 100. Is that a good proof? It's not. It's not. And the reason it's not, but I can see a lot of people making the mistake saying that if A was equal to this and if B was equal to this, then that'd be right. But we don't know. A and B are just subsets inside of those two things. So we don't actually know that. All right. So we actually have to work a little bit harder here. We actually have to think about the definitions of infimums and supremums, which you definitely want to review. And what I would suggest that you do actually is you set up a notation for the infimums and supremums of A and B. So I'm going to let alpha be the infimum of A and beta be the supremum of B. Okay? So we're going to take that. So just it just helps to have that notation. Have that notation already established in this problem. Okay? So then the claim is going to be that this supremum over here on the left side, the supremum of absolute A times B, is equal to negative alpha beta. Right? That would be the claim, is it's a supremum. The supremum of this set is that. Right? So now we have to remember, what does it mean to be a supremum? The supremum of a set has to be an upper bound for that set. That's the first part. And then there's a second part, which is where it has to be the least upper bound. Right? So you have to kind of do it in two pieces. So let's do the two parts here. So negative alpha beta is an upper bound for the set absolute AB. I have to prove this. If it's an upper bound, it just means it needs to be greater than or equal to everything in here. So we have to take an arbitrary element out of here. We have the set right here. Take an arbitrary element out of here and show that negative alpha beta is greater than that element. Okay, so let's do that. Okay, so let's just choose. Well, the elements in this set are just of this form, right? So we just pick something of that form. So choose A in capital A and B in capital B, and consider the absolute value of AB. Right. This is what we're going to look at. We are claiming right now that the absolute value of AB is less than or equal to negative of alpha times beta. In other words, negative alpha beta should be an upper bound. Okay? You guys with me? Now, the thing is, if A is somewhere in this set, then the absolute value of A is actually negative A, because A is definitely a negative number. And then the absolute value of B is just B. So my point is that this element is actually this is just equal to negative of AB, right? It's just negative AB. Right?
Why was it negative A?
Well, because look at where the little a lives. It lives in here. So what would be the absolute value of that number? The absolute value of negative 6 would be negative 6. Right? So this is actually what it is. Okay. Now we know that alpha is the infimum of capital A, right? So we know that alpha is less than or equal to little a, because alpha is a lower bound. And we know that B is less than or equal to beta, right? Because beta is the supremum of the set, means it's an upper bound. Okay, good. So the only thing that's a little bit wrong here is we need to have a negative A, right? So what we can do is just take a negative sign through this, right? So this is just going to give me negative alpha is greater than or equal to negative A. Okay, and now actually at this point everything is pretty much a positive number. So if this is true and this is true, we can literally multiply these things together, right? Okay, so the two smaller numbers, right, negative A times B will be less than or equal to the two bigger numbers, which is negative alpha times beta. Okay, and as I said before, that's what this absolute value of A times B is. Okay, so we prove that negative alpha beta is an upper bound for absolute AB. Yeah? Okay, so we got that part. Now we got to do the second part of this, part B of this thing, is to prove that negative alpha beta is the least upper bound. Okay, so negative alpha beta is the least upper bound. You remember how we approach that typically? We introduce a gamma, right? We introduce a gamma. So suppose that gamma is an upper bound. Suppose that gamma is an upper bound for absolute AB. And we need to show, we want to show that negative alpha beta was the least upper bound. So negative alpha beta should be smaller than or equal to gamma, right? It should be smaller than or equal to gamma. Okay? Does this make sense? Okay, I'm going to come back over here and erase this part. So we'll have enough room here. Any suggestions how to get this thing to work? We could use a proof by contradiction. We could say suppose that this one's greater than that one. It's one idea.
Would you need to use like an alpha, like a gamma of A and a gamma of B, where like we use the fact that.
Oh, so you want to break it into the two parts here? It's not going to be necessary to actually create two, because that's going to create more notation for us than we actually need to here. We did a problem like this. So this reminds me of the problem. I think there was a homework problem where you did something like this. You know, if A was negative, you did something like this. And so you had like an A times an alpha here, right? And then you try to show it's the infimum, so you suppose it's greater than or equal to gamma. And you might remember that problem from section 2.2 or so. What you had to do was divide the alpha over, so that then you had little a greater than or equal to something, and then use the infimum of capital A, just the set capital A by itself. So in other words, what I'm saying here is what you want to do with this is rewrite this will be, I think, the easiest way to do it. Okay, which is to just divide the beta over to the other side of the equation. Rephrase what you need to show in this format here. Okay. And then I'm actually going to also move my minus sign across. When you divide by a minus sign, what happens to the inequality? Flips it, right? So alpha greater than or equal to gamma over beta. Okay? But we need to show that alpha is greater than or equal to gamma over beta. A minus. It should be a minus. Thank you. I just suddenly thought of that. Yeah. So I need to show that alpha is greater than or equal to negative gamma over beta. Now, remember, what is alpha? Alpha is the greatest lower bound of capital A. So if we could show that negative gamma over beta is a lower bound of capital A, then alpha, by definition being the greatest lower bound, would have to be greater than or equal to negative gamma over beta. This is a relatively hard problem because I put minus signs into everything, throws everything off. It's not always this confusing. Do you understand what I'm saying? I'm just simply, what we need to show is that if gamma is another upper bound for our set, that it's greater than or equal to this proposed least upper bound. But I'm rewriting it this way so that I isolate the alpha. Okay? And alpha was the greatest lower bound of capital A. I claim it is enough to show, that negative gamma over beta is a lower bound of capital A. Just enough to show that. Because if negative gamma over beta is a lower bound, alpha was the greatest lower bound, then we'll have this. So I need to show that this is true. So given any element little a in capital A, this needs to be less than that. This is supposed to be a lower bound, so this has to be less than that. Okay? We need to show, so given any little a in capital A, we need to show that negative gamma over beta is less than or equal to little a. That's what we want to do. Okay? Gamma is an upper bound for this set, right? So gamma is greater than or equal to everything from this set here. So if I actually, let me just solve this. I'm just going to kind of do if and only if here for a second. I'm going to try and solve this one for gamma. I'm going to multiply through by beta. Notice, by the way, beta is positive. Beta is positive. And then I'm going to move the minus sign across again. So gamma greater than or equal to negative a times beta. So beta is the supremum of capital B, which means that beta is greater than or equal to, so this is going to be greater than or equal to negative AB. Because beta is an upper bound for capital B. So if I have this is just for all little b in capital B, gamma is going to be greater than or equal to that, right? Well, actually, we already know that this is true. We already know that gamma is greater than or equal. Look what gamma is, right? Gamma is already greater than or equal to negative AB. We already know that by the definition of gamma, right? So gamma is already greater than or equal to this thing. So see, we're kind of working backwards here, right? We're trying to show this part, but I'm replacing it here with these statements in between. You comfortable with that? That's the argument. That's basically it. So gamma is greater than or equal to all of these expressions. Therefore, gamma is greater than or equal to negative a beta. And so then we just rearrange the equation and we get this. That's what we need to show. Okay? So given any little a in capital A, we have shown that negative gamma over beta is less than or equal to that element. In other words, we have shown this statement right here. We've shown it. So we're done. It's a little tricky because of the minus signs and stuff. I think if I gave this to you and you had like two positive sets, everything was positive, it'd be simpler. You wouldn't have a minus sign here, and you wouldn't have to like if you were looking for the supremum of the set, it would just be the supremum of A times the supremum of B, and you'd be done, right? You could just get away with that. So, okay, so that's just wanted to practice, show you the kinds of problems. If you need to go back to the homework, you guys had a few examples like this in the homework assignment. And there was even one or two of these in the group work as well. So if you look back there, you're gonna see some nice examples. Okay. Go ahead and move on. Just trying to touch on a lot of different things here. Okay. Let's take a new problem. Okay, I'm just going to mix things up as much as I can. Okay, number 4. Number 4 here. Let xn equal 2 to the n plus 1 plus 5 all over 2 to the n. Okay? And then let's do this. Let's prove that xn is Cauchy using the definition. Let's try and use the definition to prove that this thing is Cauchy. Okay, totally changing gears. New chapter. When I say, I'm saying using the definition because of course you could prove that this is Cauchy by just proving that it converges if you wanted to, and then you just say, oh, well, if it converges, then it's Cauchy. We had that theorem, right? Every convergent sequence is Cauchy. So what I'm doing here is I'm preventing you from just doing that. I want you to actually use the definition of Cauchy. Do you guys remember the definition of Cauchy?
Absolute value of
xn is Cauchy if and only if, by definition, what is it?
Epsilon greater than 0.
For all epsilon greater than 0,
Existing delta.
No.
there exists an n naught in the natural numbers,
Such that.
such that,
If n and not less than or equal to m and n,
okay, if m and n are greater than or equal to n naught, then
xn minus the average level of xn minus xm is an epsilon.
there we go. There we go. Okay, the absolute difference is less than epsilon. Okay, everybody good on that definition there? That's the definition. One of the many definitions that I need you guys to know. Okay, so we want to use that definition. Does anybody have a suggestion how to start this thing off?
Let epsilon be.
Oh, all right. Well, that was a tough question.
Oh, it took
That
forever.
was a tough question. Let epsilon greater than 0 be given. Yes, we only start off half of our problems that way. So if you guess that's the first line, you're probably right. Okay. Good. So then we're going to look at the absolute value of this minus this. So what are we going to do next?
More than hour.
Do this part.
We're going to do some scratch work. Exactly. We're going to do some backwards scratch work. So let me come over here and set up my scratch. So basically we're going to work backwards from that, right? xn minus xm. All right. And of course I can start off by just plugging in what the formulas are here. Now, the other thing I would suggest that you can do here what could I do up here with this expression to maybe help myself out?
Yeah.
How does it simplify, guys?
2
Let's
over
see, plus
2,
5
5 over
over
2.
2 to the n, right? Very careful. 5 plus 2 over n. 5 over 2 to the n. There we go. Okay, so then I'm just gonna feed that. See, I like this. I like writing it this way because then when I subtract, the 2's are gonna cancel, right? So I'm just gonna put it in the way I see it right now. 2 plus 5 over 2 to the n, right? And then minus 2 plus 5 over 2 to the m. Oh, and then there needs to be a less than epsilon on that. Just don't have enough room there. Okay, and now we can simplify that a little bit. So this is going to be, actually I'm going to go ahead and cancel the 2's. I'm also going to pull a 5 out of the whole absolute value. So I'll do both of those things at once. It leaves me with absolute 1 over 2 to the n minus 1 over 2 to the m. Okay. And does anybody have any advice?
This is still less than epsilon, right?
Still less than epsilon, right?
And then just divide by 5.
Okay, so we can put the 5 on the other side. Very good. So 1 over 2 to the n minus 1 over 2 to the m.
Get common denominators.
The absolute value is epsilon over 5. Say again?
Get common denominator.
Okay, common denominator here. Ooh, what's the common denominator?
Still minus 2n.
2. That would be 2n plus n.
That is a common denominator. One way to get a common denominator is to just multiply these two together, right? And that's fine. So if you did that, what would you get? You'd get 2 to the n plus m, right? You multiply them together, and then you get 2 to the m minus 2 to the n. Okay. So we could do that. But let's see. See, what you often...
Can we do, instead of doing that, can we do the addition and subtraction part in the middle?
That isn't going to really be needed here. That's actually that's usually when you have two variables that are flying around, or if we had two different powers of two different numbers, we might use that, but in this case, it's just pretty simple, 2 different powers of 1/2, right? What I would suggest that we do is that we go back in our scratch and we make an assumption about the m and the n as to which one is bigger. I'm going to suggest that we make a choice there, so that it's just going to make everything a little bit easier. So I'm going to just assume that m is greater than or equal to n. You're always going to be free to do that when you're applying this definition. You can assume that m is at least as big as n. Okay. So far all of these steps are reversible. We always want them to go backwards. Is there a way, because I'm really trying to figure out how big does the m and the n need to be, is there a way to, clean this up? This is kind of hard for me to work with the way it is right now. And again, m is greater than or equal to n. We can just assume that.
Then we can just make the absolute value, we can shrink the absolute value, right?
No, we can do more than shrink it.
Can you
Can
you say it so that 1 over 2 to the n plus m is less than that whole thing? And then maybe like do some sort of a log?
So you guys are giving me two different ideas. First thing, your idea, Sal, is with the absolute values. You see, if m is bigger than or equal to n, do I even need the absolute values anymore?
No.
You don't. You don't, because this is inside here is going to be positive already. Okay, so actually, let's just go ahead and this will actually be a reversible step. So I'm going to get rid of the absolute value bars real fast. So 2 to the m minus 2 to the n. This does not fail in either direction. It's true because you're going to assume when you write this up, once you choose your n naught and you start verifying everything, you're going to, without loss of generality, assume that m is greater than or equal to n. So then this and this are equivalent. Okay. Now, if I could find something, if I can find something bigger than the left side, it'll still be, if I can find something bigger than the left side that is less than epsilon over 5, then this will be less than epsilon over 5. So can you give me something bigger than this that's simpler than
So
this?
2n divided by
2m.
2.
That's it. Just drop the minus 2 to the n. Just drop the minus 2 to the n. You don't need it. You don't need it at all, right? So this is the idea, right? If this one is less than epsilon over 5, then this one, which is smaller, right? We subtracted, yeah? We made the numerator smaller. This new left-hand side is even more less than epsilon over 5. And now this can be simplified, right? So I gotta go over here. It's a lot of scratch work. 1 over 2 to the n less than epsilon over 5. Clear enough? And this one we can flip it over, right? We really want to solve for, and I think we're going to get to Noel's logarithm here in a minute. If I flip this thing over, we're going to get 2 to the n greater than 5 over epsilon, right? So you could use a logarithm, or you could just simply say, again, you could just basically say choose n such that this is true. I'd be fine with that. Okay, or you can, you could take a log of both sides. You could. You could take a log of both sides. Let's just have some fun. We'll take the log of both sides. And then when we take the log of both sides, we of course are going to pull the n as an exponent down in front. So you're going to choose n to be greater than log 2 divided by log of 5 over epsilon. Okay? All of that is the scratch. So now you come over here and you say choose n naught in the natural numbers with n naught greater than log of 2 divided by log of 5 over epsilon. You do that, and then you just say, all right, assume m and n are greater than or equal to n naught. And without loss of generality, you're also going to assume that m is greater than or equal to n. Okay?
Shouldn't we choose n not to be greater than log 5 divided by epsilon divided by log 2?
No, I'm going to put this log 2 underneath the other side.
Right. And you have.
Oh, I wrote it backwards.
Yeah.
Oh yeah, I did that on purpose.
Like,
Just teasing. Just making sure you're staying with me here. Yeah, this should have been log of 5 over epsilon divided by log of 2. There we go. Thank you. Okay, is everybody happier now? All right, great. So, and now that you've done that, you can just simply say, therefore, thus, n times log of 2 is greater than log of 5 over epsilon, because n is greater than or equal to n naught. And now just retrace the scratch work. You guys okay with that? Okay. Now retrace the scratch. By the way, if epsilon is a big number, 5, namely bigger than 5, then this is actually a negative. The logarithm of 5 over, logarithm of something less than 1 is negative. Well, then you're just saying n naught is greater than a negative number, and that's fine. Then you just choose it to be, I've said here, a natural number, so you would be choosing it to be at least 1. Okay, so either way, you're fine, and now the argument can be reversed. Okay? You guys comfortable with that? Okay, just wanted to practice Cauchy sequences again. Make sure we knew the definition there. I'll go ahead and erase this one then. And let's try another problem. Okay, so number 5, I think it is? Is that right?
yes.
Okay. Oh man, I have so many. What time is it by now?
It's 5:22.
Oh my gosh. Okay, I have a lot of problems. Okay, let's see how this goes. Okay, I guess I could stay late and do a little longer, and then I'll just have to put a note on my door. I'll be back a little later here. So here is number 5. Let f of x equal, and I'm going to give this as a piecewise defined function. So it's going to be negative 3 if x equals 0, 4x minus 5 if x is in the open interval 0, 3, 2 minus 3x squared if x is in the half closed, half open interval from 3 to 6, union the half open, half closed interval 6 to 8, and 3 if x equals 6. Let's make this function. Okay? And the question is f Riemann integrable from 0 to 8? And if so, find the value of the integral. I didn't say by what method. I didn't say you have to, do partial sums and all, or do the upper sums, lower sums, and upper and lower Riemann integrals. Just, if possible, find the Riemann integral. Based on looking at it straight off the top of your head, do you think the answer is yes or no?
Yes.
Anthony, why do you think it's yes?
Because it looks like each piece on each interval is either Riemann integrable using theorem 6.5 or 6.7.
Okay, theorem 6.7 is the one that says the continuous functions are Riemann integrable. So you're looking here from 0 to 3, looks continuous. And this interval looks continuous. And by the time you've looked at just the middle two cases, it's continuous in all those pieces. There's just 3 specific points that are not covered by those two cases, which are 0, 3, and 6. And remember, we learned this week that if you have just finitely many points where the function is bad, and not continuous or not monotone, not Riemann integrable, then, I didn't say that right. If you have a finite number of points where your function disagrees with another function that you know is Riemann integrable, then your function is also Riemann integrable. That's theorem 6.5. Am I talking too fast here?
No.
You know what I'm saying? I'm just saying that there's just 3 points where this f of x could be a problem. And that's only finitely many. Maybe it would actually help to draw the picture. Let's try and draw a graph of this.
Pretty much all you're saying is that you have like discontinuity that you can
Remove these points.
Cover those points, then we know.
Yeah, let's try and draw a picture of this thing on the xy coordinate plane. So when x is equal to 0, the value is negative 3. Okay. Then we have this line 4x minus 5. So technically, when I put in 0 for x, we would have negative 5, but that's an open circle. And then by the time it gets over to x equals 3, it's going to be up to 7, right? Because 4 times 3 minus 5 would be 7. So 1, 2, 3, 4, 5, 6, 7. And that goes with x equals 1, 2, 3. So it's like this point right here. We're basically making this line. Okay. And then the parabola takes over. So when you put in 3 for x, oh dear, negative 25. Well, that's way down there at the bottom. I don't have enough room. Oh, and it's just going to get even worse because when I put in 8, it's going to just go down, right? So this is really unfortunate. But you get the idea. It's like some downward sloping parabola. Sorry, this is terrible. Some downward sloping parabola. Here's 8 over here. And at 6, there's an open circle. Okay? And at 6, the value of the function is 3. So this is 6, and the function fills in right there. Okay, this gives you the idea anyway, right? Gives you a bit of the idea. Okay, so the point is really that if I move this point down here, right? if I think of moving this point down here, so I can make a new function where you've moved this point here and you've moved this point here, right? So actually I would like to try to define the new function, right? So I'm going to define g of x as follows. Okay, I'm going to have to do this in pieces as well. I'm going to define g of x to be 4x minus 5, and that's if x is in the closed interval from 0 to 3. So I'm actually going to fill this hole if I do that. Okay, I'm filling this hole right here. You guys with me?
Right.
Okay, and then I'm going to I can even include 3 on that. Sorry, this would be a closed interval 0 to 3. So you see the difference? Here we had an open interval 0 to 3. Now I'm making it a closed interval. So that graph has this point down here and has this point up here. Okay, now for the part from 3 to 8, I'm going to use the 2 minus 3x squared if x is in, I'm going to use an open on 3 because you have to be careful. You have to make sure your function is well defined. So I'm going to make this into an open circle now. And I'm just going to go all the way to 8. I'm not going to stop at 6. I'm just going to go all the way to 8. Okay? Does that make sense? So just note here, guys, note that g is definitely Riemann integral from 0 to 3 because g is, well, 2 reasons. It's a continuous function. It's just this line. Or you could just say it's monotone. Okay, so let's just say by theorem 6.7 or 6.9, your choice, by either of those theorems. And g is also Riemann integrable from 3 to 8. Now, from 3 to 8, you definitely have to use the monotone condition because, see, I've defined g to be up here, and then it goes down to here. So it's not continuous on this closed interval. So, but this is Riemann integrable by theorem 6.9, I guess it is. Are some of you guys learning some of these theorems for the final? These are some good ones to study for the proofs for the final. I like these theorems. Yes, question?
So if on that segment, if that function started like going up,
we'd have to break down the 3 to 8 into multiple parts.
More
yeah,
parts.
You'd have to make it even more. It'd be even more complicated then. Okay, so then by homework, then g is Riemann integrable all the way from 0 to 8. All the way from 0 to 8. And thus, this implies by theorem 6.5, this is what Anthony was saying, is by theorem 6.5 now, as soon as g is Riemann integrable, so is f. Because f and g agree, f and g agree everywhere except for 3 points. Actually, it's only 2 points, I think.
No, it's 3.
Oh, it's 3 points. I'm sorry. It's 0, 3, and 6. Yeah, it's 3 points. They disagree here, they disagree here, and they disagree here. They agree at the 8 side, but okay. So by theorem 6.5, f is Riemann integrable from 0 to 8. Very good. Okay. So the answer here for the first part of the question is this is yes. F is Riemann integrable. You guys following me on this? This is if I ask you a problem like this is almost certainly what you're going to be using. Just a combination of theorem 6.7, 6.9, the homework problem, and 6.5. You're just kind of putting those pieces together. Did somebody have a question? Yeah.
So I'm kind of run ahead with the problems. But what I did is I defined 2 different functions with those, and then they're both continuous on the closed interval. And then you can say that f agrees with those except on us. Does that make sense? Sorry, instead of one single g, I did 2 g's.
Oh, okay, 2 other functions.
Right, and then you that should work also.
Yeah. You could just as well. You could break it up like a g that's defined from 0 to 3 and h that's defined from 3 to 8. Something like that. Is that what you're talking about?
Right.
Yeah, that would be okay. That would be fine. Now the second part of the question is to evaluate the integral, find the value. So what do you suggest for that part?
Find the value. Can you work with G instead of F?
Can you work with G instead of F? That's exactly what I was wanting to hear. Remember that part of theorem 6.5 says that these integrals are the same, right? So this is, again, theorem 6.5. So we can just work with G, which looks simpler, right? And then what am I going to do with G?
Just evaluate endpoints by
You're gonna break that up.
So we're gonna break this
From
into
can you
the
do
integration from 0
0
to 3
What?
plus the integration from
No, I was gonna say. you could-
Okay, this is the right thing to do.
You have to break it.
This is the correct thing to do right here. The problem with saying, oh, I'm going to evaluate it at the endpoints is that you have to find the antiderivative, and this is piecewise defined right now, so I wouldn't know what the antiderivative is. By doing it this way, now you can actually have the two separate formulas considered in two separate integrals. Okay, so now what do we do?
value.
You can now just evaluate these integrals, right? And to do that, you're going to use what? The fundamental theorem of calculus. I didn't tell you you had to do this the hard way, right? You can use the fundamental theorem of calculus. So what you have to do, remember the phi? You find this phi function is an antiderivative for g. So what would be the antiderivative for 4x minus 5? Okay, the power rule backwards, right? You have to trust I'm going to give you something that you can do, right? So this would be from 0 to 3. Evaluate that. Okay, and then from 3 to 8, we have a different formula. What's the antiderivative of 2 minus 3x squared?
That's 2x.
2x
X cubed.
minus x cubed. Exactly. From 3 to 8. Okay, so you can use this. This one is this is by the fundamental theorem of calculus. Ft of c is fine. Abbreviate that one. Okay, and now we just have to evaluate, plug in the numbers. This is the easy part, right? So this is going to, when I put in 3 for x, I'm going to get 18 minus 15, which is 3. And then when I put in 0 for x, I, of course, just get 0. On the second part, it's going to be a little bit bigger numbers. 8 cubed, I believe, is 324. And so 16 minus 324 is negative 308. And then minus 6 minus 27 is negative 21, so it's like adding 21 here. So you get something like negative 284, I believe. I'm trying to do this in my head really quickly. I don't know if I'm... no.
512, right?
What is?
512
Right.
is the cube.
Oh, 8 cubed? Okay, so I got all my numbers are wrong. Start over. Okay, so this one again, this was 3 minus 0. And 8 cubed is 512. Yeah, that's right, that's right. So, and then this is 16 minus that. So that would be negative 496. Okay, sorry, my calculation was not good. And then I have to subtract 6 minus 27, which is the same as adding 21. Okay, and so let's just see here. What's that going to give me? 2, 7. Negative 472. Let me just see. Oh, that's my answer. That's exciting. I got it right. Okay. Everybody good with that? All right. Okay, let's go on to another example. Are there any questions? This is a great problem. This is something you ought to make sure you study for several reasons. One is I've never tested you on it before, right? It's putting together lots of pieces of stuff that is all important. Lots of things. We did all of this in class. It's all mainstream theorems being used. So you wanna be prepared to see something like this again. Okay, so it's definitely something to look carefully at. Okay? All right, so I wanted to get that one in. Let me go on to another example. Keep plugging away here at things. The other thing you guys should probably do is go back to your midterms and refresh your memory on those. Like on that last test, I gave you some choices. Do two. If you skipped a part on the midterm, go back now and say, okay, I better look at that one. Okay, so that would be definitely advised. So in addition to everything we're doing here. Okay, number 6. Number 6. I'm going to let T be defined to be the set of A naught plus A1x plus A2x squared plus A3x cubed such that A sub I is an element of Q. Here is the question. Prove or disprove T is countable. So is this countable? That's the question here. Eric.
Are the x's also over the rationals? Or?
No, the x's are polynomial placeholders.
Oh, okay.
So these are polynomials basically. These are basically what you're looking at here are the set of cubic polynomials.
Oh, okay.
So this is a very good point. This is a set of cubic polynomials with rational coefficients. Okay? It's been a while. Can somebody remind me what countable means?
You can, it twiddles the natural number.
Okay, so i.e. T twiddles the natural numbers, or there was another possibility.
Or,
it's
twiddles
the-
Jn, where n is a natural number.
It twiddles Jn, where n is a natural number, which is another way of just saying T is finite.
Right.
So a countable set is a set that is either finite or it is in bijection with the natural numbers. That was the definition. Okay? But if you want to try to prove everything is countable just straight from the definition, it can be pretty tedious. So, you know, I guess you have to have a thought. Do you think this is going to be countable?
Q is
Yes? No?
Q is infinite.
Give people a choice, everybody will do 50-50 split every time.
Is Q countable?
It's countable, so I think so. I think it's countable. Countable.
So Q is countable, right? Q is countable, remember that? So recall, Q is countable.
Okay, what's that?
There's a theorem, right?
This is the one that this is kind of what we did on the previous semester.
So you can.
We've seen this kind of thing before.
It's a countable union of
Countable
countable sets.
Okay, if we could express T as a countable union of countable sets, that would do it.
Okay, can we form a function like, because we technically all we worry about is A naught, A1, A1.
Right. So what's the domain and codomain of my function?
The domain would be the key, it will be Q, right?
No. T. T is the domain. So you input one of these, and then you spit out, and what did you want to spit out?
The Q.
Q times Q times Q times Q.
Right.
Q times Q times Q times 2. That's the idea, right? So because you said you wanted to spit out all of the scalars, A naught, A1, A2, A3, right? And so what is the formula here for this? Well, this is just going to be f of, you take one of these cubic polynomials here,
And it's
and what are you going to spit out?
A0, A1, A2.
4 slots, right? A0, A1, A2, A3. All right, beautiful. Okay. What do you want to tell me about that function?
It's also
It's on
It is onto. True. What else do you want to tell me about that function?
It's countable.
A function can't be countable.
It needs to be 1-to-1.
It's 1-to-1.
Because
So this is actually a bijection.
Right.
See, these things twiddle each other. Now, do you remember? So if two things twiddle each other, and one of them's countable, then so's the other. Or if one of them's uncountable, then so's the other. Right? If they twiddle each other, it isn't even necessary that they twiddle each other. If you which okay, so I just want to get this straight. We're trying to decide if T is countable. Do we know if this one is?
yes.
This one is countable, right? So this is countable. If you wanted to explain why, you have a couple of choices. One is you can just simply cite a homework problem where you prove that if A is countable and B is countable, then so is A cross B.
And you can-
Right, so you could just mention, so you could say this is countable by homework, Or another way to do it is to express this as a union, as a countable union of countable sets. You could do that as well. So you could say, let's see if we can actually try and write it. You could write this as a, so basically you're going to do like A, B, C, and D is going to be a union where D is in Q, right? And then within that, you're taking a union as C is in Q, right? And you have 4 unions here, right? So you just go backwards. I ran out of room again.
Would you be
So-
able to do that directly to to T itself? Or
You could, well, T has plus signs in it though, so you're doing algebraic operations here, whereas in the set, you don't have any algebraic operations. So it's actually, I think, more favorable for, because the concept of countable is really a set theoretic concept. There's no adding or subtracting going on. So it's actually better to render this in this format here. So is everybody okay with this? This is a countable union of countable sets. And that's because, well, you only have one set, right? This is just a single element, right? This is a set of size 1, right? So it's definitely countable. And how many things are you unioning together? Well, it's always a union of a countable number of things. So theorem 2.4. So this is countable by theorem 2.4. That's one of your theorems that is in the list of big theorem. Those 7 theorems that I've given you as a list to learn, those are like 7 of the most important things. I wouldn't be asking you to memorize and really study a proof of something that wasn't a big deal. So this is a big deal for those people who care about countable and uncountable sets. Okay, so this one is countable. So now I have a question for you. To show that T is countable, knowing that this one is countable, do we need to know that F is onto, or do we need to know that F is 1-to-1, or do we really need to know both?
1-to-1.
We need to group both, right?
It's 1, 2. I think R is
Yeah.
enough, right?
You don't need to have both. You only need half of the condition. So the way to excuse me, the way to remember it is, if you have a function that is onto, it goes from a big thing to a small thing. This is for onto.
Oh, so it's 1.
But for 1-to-1, you're going like this. Okay? Now at the moment we know that the second set is countable. We want the first set to be countable. So which of these two do we need to have?
1.
This is it, right? Okay, because guys, if you know that this one is countable, but you had an onto function, well, the A could be much bigger. Who knows? It might be uncountable. But over here, if your bigger thing is already countable, and you're into a smaller thing inside of it, then that smaller thing is also guaranteed to be countable. I mean, you guys, you have, it's proposition 2.8 and 2.11. You can look back at those propositions, but there's a bunch of statements there that you have to memorize, or you can just use these pictures to help remind, oh, you know what, I think I have this maybe wrong. It might be, I think it's 2.9 and 2.12, I'm sorry. Let me just double check that. I think it's, yeah. Yeah, 2.9 and 2.12 is what I should have been saying there. So you can look back at those propositions if you want, but I actually think it's easier to kind of just draw these pictures to help you remember it. Okay? Great, so therefore, right idea, we define this function, define your set, which you're trying to decide, map it to something that you know is countable or uncountable, and then from there, use those propositions. Yeah. Does this make sense? So that's really the best way to do that. Okay, great. Let's go on, do another problem here. Number 7. Okay, so here's number 7. just mixing up lots of problems. Define f from R to R via f of x equals 1